is indeed due to a planet, right? Could tell me it's what, about 50 days? Yeah, it's 45, right? That's not Kepler-10b, okay? But it is a transit signature of a candidate that's a little bit further out. It's orbiting at 45.29 days and would have a radius of about 2.3 times the Earth's radius. All right, so where's Kepler-10b? Where's the signal of Kepler-10b? Well, to show you that, I have to zoom in. So what I'm going to do is I'm going to take this green vertical area right here, and I'm just going to zoom in. I'm going to expand that. So in the next plot, all you're going to see is one of these blue lines, and then you're going to see all of this up and down here. And that's what it looks like. There's the blue line. Okay, nice big transit here due to a 2.3 Earth-size planet. Do you guys see another transit event in there? It's not as easy to see, right? Here, there's one here. I think we missed one in here, 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 here. Let me mark them with horizontal lines for you. Now they're obvious, right? Okay, again, these, I would say, are very easy to see. I didn't have to do any averaging to be able to pull that signal out of the data. I can just see it. I can just plot it and see it. It's just obvious, okay? And this signal is only about 40% larger than what you would expect from a real Earth-sized planet, okay? But the orbital period, look how short it is, 0.84 days. This thing orbits its star in just 0.84 days, about once a day. Right? Okay. Now, once you see one of these things, it doesn't necessarily mean that you've discovered a planet, because there are astrophysical signals in nature that mimic planet transits and confound us. And we have to do a lot of follow-up observations from ground-based telescopes and additional analyses with Kepler data itself in order to vet out these mimicking signals, these astrophysical false positives, we call them, from bona fide planets, okay? This is an example of something that confounds us. Here we've got this big star that we're observing, but we're observing right in the galactic plane pretty much, right? The density of stars is very high, and almost always there's another star that's dim. It's probably very far away, but it just happens to be kind of aligned. And so the light, when we measure this, all we see is just a blob of light in a pixel, right? We don't resolve that there's more than one star there. And so all of that light gets put into our measurement. And if this thing happens to be an eclipsing binary star system or something, and it adds a tiny percentage of light to the whole, it could look a lot like a planet transit signature. And so we've got a lot of different analyses that we do to vet them out. We have a plan for vetting them out. But that's what distinguishes a planet candidate, which is simply a star that has something interesting in its light curve, from a bona fide planet, confirmed planet candidate. Sorry. Okay, and so we use many ground-based telescopes to do this work. Everything from, the 2-meter kind of class telescopes at Tillinghast, the Tillinghast reflector here, the 3-meter telescope at Lick Observatory, to the Hobby-Eberly telescope in Texas, and our big workhorse, which is the Keck 10-meter telescope that's on Mauna Kea. And that's interesting, because what happens is we've got our transit measurement that tells us something about the radius of the planet, right? How much light is being blocked out tells you something about the radius. And our ground-based observations that we take with Keck Observatory can have the potential to tell us the mass. And if we have the radius and the mass, then we've got mass divided by volume, which is density. And for Kepler-10b, the radius turned out to be 1.4 times the Earth radius. The mass turned out to be about 4.5 times the Earth's mass, and together those give us a density of 8.8 grams per cubic centimeter, with very tiny error bars. And it's because of that density that we know that this is a rocky world. What's the density of Earth? Does anybody know? Water, what's the density of water? 1. Water's 1 gram per cubic centimeter. And that's about the density of the giant planets, Jupiter and Saturn, right? Earth is more like 5, okay? This is 8, 9 grams per cubic centimeter. Okay, So now what we're going to do is we're going to take the mass and the radius that we got and that density, and we're going to compare it to theoretical models. And we're going to say, well, what kind of a composition could produce that mass, radius, and density? Okay? And so here I've got a plot, and I've got radius of the planet versus mass of the planet. And I've got these theoretical lines, these theoretical curves. And you'll notice that one of them is called Earth composition. And so basically all that means is if I take a mix of materials that produces an Earth, and I double the recipe, and triple the recipe, and quadruple the recipe, what do I get? What mass do I get? What radius do I get? And so if I just scale the recipe like that, all of the mass and radii should combine to follow this curve. This is the Earth composition curve. And indeed, you've got Earth there, and Venus there, and Mars there. As you go up in mass, you also go up in radius, and there's Kepler 10b. And it's displayed as an ellipse because the size refers to the uncertainties.